There is an annoyingly prevalent myth in the mobile phone world.
Visually speaking, you're not really going to be able to benefit from those extra pixels on the phone's display, even though it is a much higher resolution.
4K screens on the phone is just a waste of battery life, and you'll never notice the difference unless you pixel peep with your eyes glued to the screen.
I've said over and over that the near 4K resolution on the Xperia 1 series is overkill in the extreme.
So the myth is that it's not possible for a human to perceive the full resolution of a 4K display on a mobile phone. While I've only included a small subset of channels that I regularly watch and respect, this myth is widespread, so it seemed valuable to really cover it now. I'm going to start off by putting two assertions to you, and I'm going to back them up throughout the video. 1. Looking at fine details on pictures and videos is exactly the wrong way to test whether or not you can perceive that 4K resolution. And likewise 2, the default configuration on Sony's old phones for when to use 4K versus when to use 1080p is the optimal worst way to use that technology. My understanding is that they fixed this with their more recent phones, although I haven't had a chance to test this. Phew, so those are some big words. Let's get into this. There are various units of measurement, but by far the most common one is pixels per inch, so that's what I'm going to be using here. Effectively, a high pixel density is when you have the pixels very tightly packed together, versus a low pixel density where they're very loosely packed together. If you make the display size smaller, you're effectively making their density higher because the pixels are closer together. Conversely, if you make the display larger while keeping the same resolution, then you're effectively making the density lower because the pixels are more spread out. The relevance of this is that the myth really started to gain traction when a 5.5-inch display on a phone was quite large, and now it's quite small. So the display sizes have been getting larger, meanwhile the resolutions have been getting lower, which means that two different factors are reducing the display density. So to put some numbers on how much it's going down, this phone here has a 4K display on it, and it has a PPI of 807. This phone has a 1440p display, and it has a PPI of 568. So compare that to the more recent Sony Xperia 1 Mark IV, that has a pixel density of approximately 643 ppi, so it is much closer to the 440p display of several years ago. It seemed like time for a proof of concept, so I wrote a quick Android application which just had a few little test patterns. The reason I did this rather than using photos was because I didn't want there to be any possibility that compression or any other assumptions could be getting in the way and influencing the result. It also meant that I could animate the pattern in a predictable way. So I built the app, stuck it onto my phone, and I couldn't see it. I could see it moving, but I couldn't see which direction it was facing. Am I wrong about this? Well, if we have a look at how much video is remaining, that's a bit of a clue. So, let's dive into it. The first thing I wanted to understand was, what was the display actually displaying? So I pulled out one of my old cameras from 2006. It's a 6 megapixel job. It was always very low end, but its macro was pretty good, so it was really good for this task. It does have one limitation, which we will discuss later on in the video. My initial setup had the camera on a tripod and the phone on a little mini tripod, and I would then put the two things together and I'll take the photos like that. This had so many factors for inconsistencies and errors that it just wasn't worth continuing. So what I ended up doing was putting the phone flat on the table and then facing the camera directly down on top of it, and then I had much finer grain control. I could control the phone remotely, so then I could iterate the pattern, and I could control the camera via timer, so I was able to be completely hands-off from the whole setup. I was able to remove all the bumps and wobbles and all the inconsistencies. I used the focus of the camera to determine how far the camera was away, so therefore all of the patterns between all of the different test shots and all the different phones, I've got them pretty close to consistent, so we can compare them side by side quite nicely. So, it was time to look at the results. Okay, so at this point we need to discuss Pentile displays. If we have a look at what we think of as a traditional RGB display, you have the red, green and blue, and they're all very close related to each other. You have one complete set per pixel. So if you have a pixel over there, it's got a red, a green and a blue. And you have a look at a pixel over here, and it's got a red, green and blue. And that's all fine. Pentile displays share some of those elements. And that comes with a whole heap of advantages and disadvantages. So we probably need to dive into that a little bit now. The first thing that surprised me about Pentile displays is that I thought they were a fairly niche thing. I thought it was just a few Samsung devices and that was about it. In my testing, of all the phones I tested, there was exactly one device that was not a Pentile display. And I ended up going and doing a bit more reading on Wikipedia, and it said, as of 2021, almost all OLED screens and portable consumer devices use some form of Pentile subpixel layout. So yeah, that very much mirrors my results. So that's quite interesting. LCDs don't have to have a rectangular layout like this one does. They can come in all sorts of different forms. This 4K Sony is an excellent example of that, where it's using a sort of hybrid between the two, and we'll look at that a bit more closely in a moment. So most displays that you're going to be looking at 1080p or above are going to be Pentile, and that makes this next section very interesting. So Pentile displays have a number of pros and cons. One of the big ones is that because the elements are being shared between multiple pixels, the subpixels are not necessarily in a straight line. This can actually help reduce the screen door effect. They can be cheaper to manufacture because there's less complexity for a given resolution. If they're designed for it, they can be amazing at doing different resolutions that aren't necessarily multiples of each other on the same panel. Pentile displays can have better luminosity, and that's a bit more of an involved conversation, so we'll just leave it alone for now. They tend to do better at having less colour bleed than what we think of as traditional displays. For example, here you can see there is some red and some blue on both trailing sides. Whereas if you have a look at this Pentile display, you can see that the shape is pretty smooth, but also the colours are well balanced. But that's not some universal truth. Have a look at this one here. They could have balanced the colours, but they didn't, and I don't understand why. They probably had their priorities elsewhere, I guess. Pentile displays tend to have fuzzier edges than non-Pentile displays. This is because subpixel elements are shared between pixels, which means that the boundaries between one pixel and another are less clear, and they're also less consistent. So Pentile displays rarely benefit from a higher resolution, so that these defects become less visible. So while edges may not be as defined as non-Pentile displays, they do handle shapes really, really well. That's because they really thrive when there's lots of neighbouring pixels right beside each other, because then they can really optimise for that shape and keep it colour balanced and smooth. I spent weeks looking at close-up photos of phone displays. I could talk for hours about all the interesting tangents that went on exploring how these worked, but there's a few specific ones I want to call out. Have a look at the Samsung. You can see that vertically we've got one single pixel width. But then when we look horizontally, it's actually two. So these two lines here, those are supposed to be one. However, we want to draw somewhere in the middle, and we don't have any red pixels in between there. We have green ones, but we don't have any red ones. So we have to straddle it, go either side, and that's why we get two dim lines rather than one straight clear red one. And that's a good example. You can see that with red and with blue, we sometimes get that division like that. But with green, we don't.
Whoa, Future Kev here. It's a bit more complicated than that. It deserves a whole blog post by itself. But just to sort of highlight a little bit here is what we think of as a traditional RGB display. And you can see the red, green and blue, that's one-to-one mapped and everything's coming through cleanly. And then if we go and have a look at a Pentile display here, at another Pentile display here, and you can see these ones are behaving completely differently again. So just understand that this behaviour varies between different types of display. It affects red, green and blue, and it affects horizontal and vertical. Anyway, with that, let's get back to the video.
Now look at the Sony 4K display here and notice that the white dots are not going straight. I would have expected them to be all diagonal one way, and just continue for the whole display like that, but they actually alternate every few pixels. I don't know why they're doing that. My best guess is that they're trying to make sure that any distortions caused by the Pentile layout is not uniform throughout the entire display, and so then that sort of diffuses and disguises the problem. I've got a few minutes with some family to photograph their phones, so then I'd have a more diverse library of phones that I've looked at. With other people's phones, I specifically haven't been changing things like the system font size or light mode versus dark mode, so these can't be directly compared to my other results, but we can still make some interesting observations from them. I was really happy to photograph an iPhone 12 Pro because those displays have been talked about for so long, and it was just really interesting to see what do they actually do. I was actually surprised. It was better than I was expecting it to be. One of the things that they've done really well is that the space in between the subpixels is very small. There's very little black there. This means that as hard as you look, you're going to really struggle to find any screen door effect on there. In fact, I'd go so far as to say you could probably lower the resolution of that quite a lot, and you would probably still not get any screen door effect on there. The other thing that I thought was really interesting with the iPhone 12 Pro is that I'm getting some alternating colours there. I originally thought this was a limitation with my camera, and we'll go into more detail about that in just a moment. But you can see on this photo, the whole area is really nicely covered. It's all showing, all the colours are showing correctly. So I think it was just simply an interaction with the refresh rate versus the shutter speed. I think that phone has a variable refresh rate, so it could well be some factor along with when one of us last touched the phone versus how long it took me to take the photo. The Samsung Z Flip 3, that was really interesting as well. It was my first time looking closely at a foldable, and they have definitely prioritised different things to the other phones that I've looked at. This one surprised me to the degree that I thought that they weren't actually using the subpixel resolution and they were just simply going, right, here's a block of 3, here's a block of 3, here's a block of 3, but that's not actually what they're doing. It was only after I'd spent a fair bit more time exploring the photos that I'd taken that I got the answer. Yeah, it is using the subpixel resolution, but it's not as obvious as it has been with almost every other phone I've taken. For pretty much all of the phones that I've looked at, this is true, but especially with these two phones, it would be really interesting to spend a lot more time diving in with more test patterns and sort of exploring what they do to really understand what they do. But what I got was really interesting to see, so it was definitely worthwhile. The last thing I wanted to comment on with this display is one of the complaints that people have had with some previous Samsung devices was that the colour saturation on the OLED displays was too strong. And that complaint is often said by cheap budget phones that have OLED displays as well. But you can see in these test patterns here that, sure, I'm displaying these pure colours, but we're also getting some neighbouring subpixels coming in there as well. Now, once again, this is something that I would explore more if I had more time with the phone, but I don't know whether it is Samsung going, hey, look, we can make the things a little bit less saturated if you want, or whether it is, hey, we need more brightness, let's put all the hands on deck and we're going to get as much light out as possible. I mentioned limitations of the camera, so let's cover that now. So far we've talked about patterns that are used for displays, but the same sets of tricks are actually used on cameras. The assumption goes that we have much more sensitivity to the brightness of light than we do for the colours of light. So therefore, more of the resource available is put into determining the brightness of the light than the colour of the light, and this determines what layout we will use on the sensor. This is called a Bayer filter pattern. So while this gives us the advantage of better representing what we see well and not focusing so much resource on what we don't see well, it comes with a consequence that the colour resolution does not match the brightness resolution, and so recombining those two things together can be a little bit tricky, and when it's done poorly it leads to colour bleeding on fine detail. But the important thing to note here is, as you approach the limit in the resolution of the camera, the algorithms that try to match up the colour and the brightness start doing the wrong thing. The most notable example of that is with the Sony 4K phone. When I have a single pixel, I can very often capture the red, green and blue components separately. But as soon as I start having other pixels on the same line, then that whole thing falls apart and we just get the final colour that we were supposed to see all along.
So at this part of the video, I was going to be interrupting and telling you about, hey, I've just improved the technique, and it looks like this, and show you this nice macro shot. And then I got as far as editing that, and then suddenly I was like, bing! And now I have footage that looks like this. So now I can get really, really close. But this is pushing the limits of what I can really say that you can do with consumer gear. But just know that everything else in this video is done with very old consumer grade hardware. So this is stuff that you can do yourself if you want to. But it's been really cool to get these closer shots here to just sort of really get some nice quality stuff here. This is so close that in some of the videos you can actually see the defects of the subpixels. The catch is that it's very, very time consuming to get these shots and very fiddly and frustrating. And you don't actually know until you review the footage whether or not it's actually good enough. So I've stuck to my main technique for this video, which is very easy to do. And this technique here is going to be worth a video all by itself because it's freaking cool.
Alright, so we've looked at this from a whole heap of different angles now. Let's take it up a notch and look at fonts. For all of these examples, I have adjusted the system font size so that they match the same physical size across all of the displays. The size that I've chosen is the size that I find most comfortable to read on a phone display, and it's noticeably smaller than the default font size. Matching them up was easier said than done, but in going to this effort, this allows us to match them up side by side like this, which makes it really easy to do some comparisons. Let's start with what we think of as the traditional RGB layout. Notice how the font rendering engine is trying to smooth off the edges of the font. It's doing this by sending incorrect color values to the display, and then that means that the different subpixel elements light up or don't light up accordingly. This is what gives you that colory speckledy pattern around the edges of fonts that you see sometimes. This technique can improve how good fonts look by quite a considerable margin, but it requires the font rendering engine to know exactly the layout of the display. So one set of configuration can't simply be taken from one display to another and definitely work correctly. Now let's go and compare this to the Samsung S6 Edge. Notice how the font's starting to get a bit smoother, the edges are getting a little bit rounder, and there's a little bit less color bleeding. But now we go over to the S8. This is almost the same display density as the S6, but notice how smooth those fonts are now. They've done a really good job of anti-aliasing around the edges there. There's very little color bleeding and the edges are very well defined. Also notice how the shape of the font is beautifully preserved. Meanwhile, it sort of falls off. I think they've tried to mimic a ballpoint pen here, but that's just speculation. Notice that the very edges are not quite as well defined. I haven't spent enough time with this display to actually work out what my opinion is on it. My gut feeling is it's probably pretty good. It looks good. But like I say, I'd have to spend more time with it to really have a strong opinion. And now let's look at the 4K display of the Sony. Notice how sharp and round the edges are compared to the 1080p display. Let's try something slightly different. Let's look at some straighter characters like these. Notice how on the 4K display, still looks good. Same on the Samsung. But look what happens when we look at the 1080p display. Some of it is clear, and some of it is not. This is from a niche device where the display was not the focal point of the device. So I fired up a 1080p Pixel device in the Android Studio and configured the font so that it would match up with the other phones that I'm testing. And look at this. So it's happening in software there before it even gets to the display. So this blurriness is one of the manifestations of the blurriness that I see when I'm using a 1080p display. I actually had a really interesting conversation with a friend about this, and while we disagreed about which platforms we thought were better, he made a really good point that this might be fixable in software. It depends why the character is overflowing into the next row of pixels. If it's spacing or letter sizing, the way that could be fixed is different, and the consequences of fixing that could be different. And it may well be that the developers have consciously decided that a little bit of overflow is better than wiggling the spacing between the characters or making the letters uneven sizes. So assuming that they have made those decisions for those reasons, then having a higher resolution display is actually going to solve that problem. So we've talked about text edges. I'd like to bring up one more use case where I find the resolution very noticeable, and that's when I'm using a remote desktop. I find it very helpful to be able to zoom in and out of the desktop, and having a much higher resolution makes it much easier to find a scale in which the fonts and everything are easy to read. Conversely, the biggest drawback of higher resolution displays, which pretty much everyone brings up when they're discouraging it, is that you're having to manage a larger number of pixels, and so therefore that is more of a resource strain on the device. So let's get into that now. I haven't done any explicit measurements on this, but here are a couple of observations. In the time since the XZ Premium came out with its 4K display, SoCs have become faster and more power efficient, batteries have got bigger, and screens have got bigger. Anecdotally, it's got a 5-year-old LiPo battery in it that's a fair bit smaller than the batteries that we get in modern phones now. And just to hit that point home, this is a LiPo battery that has aged by 5 years, and yet it is still an all-day phone, despite doing a fair bit of YouTube each day. Coming at this from another angle, I'm not a gamer, and gaming has very different requirements to my use cases. And there are many other use cases that people have. So, for all these different use cases, the priorities are probably different. This project has had a lot of tangents, and so has this video. So let's have a moment of cuckoos to celebrate the tangents. Okay, that's enough. So over the course of this video, we've talked a lot about techniques which are used to trick the brain into perceiving more detail with fewer subpixels. Those tricks require strong signals, i.e. strong contrast. So when I said, 1. Looking at fine details on pictures and videos is exactly the wrong way to test whether or not you can perceive that 4K resolution. This is why. We need high contrast to make use of the resolution, i.e. not photos and video. If you have a look at photos and video, let's take a look at this example of one of my previous videos on YouTube at 4K. My glasses look pretty sharp, so let's go and zoom into those. And you'll notice there is not a single pair of pixels that have a sharp contrast in there. Despite the picture looking crisp, it is not a sharp picture. That is the nature of compression on the media that we can see on our phones. It is technically possible to get something that is higher quality. That is not the norm, and so that is not how we should be testing it. So to be a little bit more explicit about that, it is very hard to get photos and video that do not have compression artifacts in them. And when you're using material, that doesn't matter. If you want to perceive that 4K resolution, that compression is not working in your favor. When I mentioned, and likewise too, the default configuration on Sony's old phones for when to use 4K versus when to use 1080p is the optimal worst way to use that technology. Those phones defaulted to 4K on YouTube, the album, and a few other Sony-specific applications, and everything else was 1080p. As I just showed, that's the exact opposite of what you want if you want to experience the clarity of a 4K display. Photos and videos are just not going to cut it. Text and algorithmic animations, such as live wallpapers, are much more likely to give you a good result. So that's cool and all, but it would be nice to help you experience some of this for yourself, and I'd really like to have some data on how many other people notice this as well versus how many people don't. So I've made an app where you can test yourself, you can see the results, and you can submit those results anonymously. If you don't have a 4K display on your phone, you're not going to be able to get all the way down to the 4K experience, but you'll at least be able to get close. But if you manage to get down to 1 pixel, that would be very interesting for you to try a resolution, because the Pentile display is not well optimized for displaying just a single pixel. It's better for displaying shapes. So if you are seeing 1 pixel width, that demonstrates that you are seeing the display very well. And while the geek in me wants to have all of the pixels, I get it. It makes sense. This is how we use a display. At the times when we need the clarity the most, we need the shapes to be clear and refined. It doesn't really matter if we see an individual pixel or not. In fact, it's even better if we don't see an individual pixel, because when it gets to the point that we actually can't see it, then we really are getting to the point where we're getting really smooth edges. On that note, in testing, I've tried to be fair to test the effective resolution while not being disadvantaged. So that's why I've tested a step rather than an individual pixel. When you complete the tests, you get a few questions, all of which are optional, but if you'd like to fill them in, it would be very helpful. And then after that, you get a comprehensive report. You can also go and have a look at the test patterns that I used in this video. And the picture on the home screen is 2 pictures. One is my preferred font size on a 1080p display, and the other is that same physical font size on a 1440p display. Let me know in the comments if you'd like to see a follow-up with all of this data. Also, what would you like to know in that video?
Let's quickly recap some of the important points before getting to the point. All of this video has assumed that you're holding your phone at a distance that is comfortable to read at. Otherwise, what's the point of even discussing this? I haven't covered AR/VR because I doubt that anyone actually contests that benefit, and this video is already really long. Resolution, display size, display density, the distance to the display are all closely linked for the purpose of this conversation, and I've made an explicit effort to be upfront about those throughout the entire video. Some of the benefits of having a 4K display on a phone: text clarity, particularly at smaller sizes. Some of the issues with text clarity on lower resolution displays could actually be addressed with optimizations in the font rendering engine. But we need to remember that those optimizations will come at the expense of some characteristics that affect readability. For example, consistent character spacing and consistent character line width. A higher resolution does not make those sacrifices. Color balance on sharp edges like fonts. Usually color balance and sharpness on a Pentile display are opposing forces, whereas when you increase the resolution, they're not. Scaling highly detailed raster images, like remote desktops, works a lot better on a higher resolution display. This is important because, let's face it, when you are doing a remote desktop on a phone, you are typically wanting to have text that is actually readable, meanwhile wanting to only focus on a few things at a time, and it is really valuable to be able to lay things out on your desktop and then just pan and zoom around as necessary. Testing what you can actually see. Video and images are not good ways to test what you can actually perceive, because it's very rare that you actually have enough contrast there to actually make use of the resolution. Text and natively drawn vector graphics, for example some live wallpapers, are much better for doing this testing because they naturally have much higher contrast in the edges. And I've written that app to help us quantify exactly what each one of us can and can't see.
So in summary, what's the point? I'm not trying to tell you that you need a 4K display on your phone. I'm not trying to tell you that your phone is rubbish. And I'm not trying to tell you that your priorities are wrong. What I am trying to tell you is that the rhetoric that a human cannot see the detail of a 4K display at reading distance is just simply wrong. If you can't see the difference, that's fine. Enjoy whatever display you like on whatever phone that fits your priorities best. As for me, I do see the difference, and as you may have noticed, I have other visual challenges that are not focus related. Some days that gets better, some days that gets worse, but it makes sense to me to eliminate as many of the other challenges as possible to give myself the easiest chance of being able to read well. And clearer text is a tool to help me do that. Recently there has been a rhetoric in many subjects that resolution doesn't matter. Resolution isn't everything, but it sure is a contributing factor. If you're a reviewer and you don't understand why someone would want this, that's cool. Just present it as your opinion that it doesn't match what you want. But please don't present it as this universally unusable thing. It has been so disheartening to see the number of options shrink and get confined to just a few niche devices that are really expensive, because groupthink has effectively told manufacturers not to bother. Give the app a go and see if you can see it. If you can't, enjoy the lower-end devices. If you can, I hope you'll revisit your opinion. It's been really interesting to see the different implementations from one brand to another, and why we see different artifacts depending on which solution is implemented. The real eureka moment for me was watching family members try my app, and being able to confidently see the detail first go. That was really cool. It was that whole thing of, am I actually insane? And getting that validation was really nice. This project has taken me down many rabbit holes. And there's still quite a few that I haven't explored, and I would love to explore in the future. I don't have time now, but it has been so much fun. I'm expecting there's going to be a fair few questions on this, so I'm going to provide updates on my blog, and if there's enough questions, I might end up doing a follow-up video, and if there's enough interest in a follow-up video for the data, then I'll do that as well. But again, the blog is a one-stop shop where you'll be able to find everything that is there. So in the meantime, let me know in the comments what you would like to know, what you'd like to see, and I'll do my best to follow up. So anyway, I'm RandomKSandom, and this has most definitely been a project that fascinated me.